Okay, so I hope it's recording now. Um, this is going to be a hard video to do. Uh, I I usually post high school um, and under mathematics and science. Um, I uh, did an undergrad degree in physics, so I did it at the University of Toronto, and I remember switching. So I started off in life science in first year, and I loved high school physics, and I wanted to go all in with the physics courses. And there were so many interesting courses that I had to take, and I took. So you have a major in university, but at the University of Toronto, you have an option to take a specialist. And so what I did was I took the physics specialist and a math minor. And you have to choose that subject post in second year. So I did that, and I remember that was 2008. So I ended up taking a full year of physics for the first time in a while, and one of the first courses I had to take was Intro to Quantum Mechanics, and I ended up taking as part of the specialist program. It's compulsory. You have to take these classes. Um, I ended up taking 3 years of quantum mechanics, and I will admittedly say that even after 3 years of doing this, I didn't know it to the level of some expert. I wasn't that good, but it was very very interesting. I remember taking a midterm exam for Intro to Quantum. This was the first full quantum physics course I had ever taken. And I remember talking to my friend Jason at the time, and I was like, Jason, man, I feel like I don't know anything, but I feel like I know how to calculate. I know how to calculate the answers to the questions, but I don't understand what is actually being told to me. And so this isn't me, I guess, lecturing and like teaching you as if I'm some, know it all. I'm not. This is actually a part of the process of my learning as well. As I'm a TA, I'm a teaching assistant, and it's you learn so much by teaching, so much, and I find it remarkable that I've learned so much through teaching, much more actually than by learning in class. So I'm using the quantum mechanics. This is the book I used. This is the literal book that I used. It's Quantum Mechanics Intro by Griffiths, and it's the second edition. So we're talking 2008. I probably have to update my collection a little bit, but I really enjoyed this book. Um, I did pretty decent in my first midterm. It was like an 80%. Got an A minus, but again, I feel like I had no idea what was going on. So why don't we get started? Just as a prerequisite knowledge that I'd recommend is for sure know something about classical mechanics, classical physics. So I can kind of give an intro. Hopefully that helps. But so when you are dealing with classical physics, you the goal is to know a ton of information about, say, some particle with a mass m, right? So you need to know its position. You need to know its momentum, right? Or velocity. Actually, let's do that first. Let's do velocity. So it's velocity, and if you've taken a calculus, you'll know that the first derivative, right, the rate of change with respect to time of the position function is the velocity function. Once you know the velocity function, you can know its kinetic energy, right? Because that's half mv squared. What else can you know? It doesn't go into it, but there are other variables that I'm sure you can uh, discover. How do we get there, though? How do we get the position function? Well, what you can do is you can solve Newton's second law, F equals ma, and a is the acceleration, F is the force. And the acceleration is the second order time derivative with respect, well, I already said time. So second order time derivative of the position function. Now, how you make a connection between this and quantum mechanics has to do with what is called the Schrödinger equation. I'm sure you've heard of Schrödinger's cat experiment, thought experiment. Schrödinger had written down a wave equation, and that wave equation had this quantity psi in it. And for the life of me, I don't remember what it is, but let me write it down. I've got it in my book. I h bar, first time derivative with respect to psi, negative h bar squared. I used to be able to remember this equation, just out of like, it was just a part of my memory at the time. I had studied so much. Plus v psi. Okay. Now this psi here is the wave function. H bar is reduced Planck's constant. So Planck's constant is a value. I forget what it is, and I don't recall the units, but you can look it up on Google. H bar is reduced Planck's constant, which is Planck's constant h divided by 2 pi. So be careful of what constant you're using. Make sure that if it's Planck's constant, you're not actually using reduced Planck's constant. You've got the mass, and you've got this v here, and that v is a potential energy function, right? It tells you information about the system, particularly whether or not it's a conservative system. So basically, in classical physics, you can determine a particle's position x. In quantum mechanics, with the word wave, what that means is you actually won't be able to determine the position of a function. You'll know instead the probability distribution for that position. What that means is you'll know with some probability where a function is between, say, a and b, but you won't know with a certainty. So that's how it relates. When you go from the classical physics, the macro scale, to the quantum scale, you lose that certainty, right? And that kind of ties into the Heisenberg uncertainty principle. But so Griffiths goes into a marvelous... Griffiths talks about the interpretation for the wave function, which I think is kind of nice. If you take the, I forget what it's called, I think it's the norm of psi, and you square it, the integral of that between a and b, and if you have no idea what that is, don't worry. With respect to x, if you take the integral of that, the area under the curve, let's say psi squared is some function, then you've got 2 points, a and b, and when you take the area under that, that is the probability that the particle will be between a and b. All right, so let's see if I got that. Yeah, so that is the probability that the particle will be between a and b. That is actually Born's statistical interpretation, right? Because it seems kind of weird. It's like, so psi, right? If you look up at the above equation, psi depends on t and on x. So if we're dealing with a particle, why is it that you have a particle which should be a defined point in space and time? Why is it that it has this kind of dependency on position? Shouldn't it just be at one point? Shouldn't it be invariant in position? and it's not. The Born statistical interpretation connects the idea of having a particle and with position and time in this wave-like nature. So that's an intro to the wave equation. Now, because you're dealing with a wave, again, you're dealing with not knowing with a certainty what the position is. So it has this wave-like nature, but if you were to measure its position, and it just so happens to be at position C, let's say, when you measure it, it begs the question, what is the position of the particle before you made the measurement? So there are three schools of thought. One is the realist position, right? And the realist position is basically it was at the particle was at C the whole time. Now, the problem with that is that if your theory is telling you that you at best know statistically where it could be and not where it is, then the realist position states that the theory is incomplete. You need more information. Maybe there's a hidden variable that that could tell you more information about its position, and you just don't have it yet. There's the orthodox position, which is probably something that you heard of if you've ever heard of the Young's double slit experiment. The orthodox position states that the particle is, so once you take a measurement, the wave function collapses to a spike or a delta at C. And that's the orthodox position. That's basically what you learn in quantum mechanics these days. And that's that once you repeat a measurement, you stay at C. And C is the measurement if it's done quickly enough. And then other than the orthodox, there's in a religious fashion, there's the agnostic position. The agnostic position is states that you don't know. You don't know what the... it kind of says that it's irrelevant to know what the position is before the measurement, because the only way to find out what the position is to measure. So it's really unimportant to know what the position is at a point prior to measurement, if that makes sense. So these are the three schools of thought. I hope this is a good intro. I'm going to leave these notes available. I'm going to provide a link in the description. I hope this was a good intro to quantum, just to touch on it a little bit. Again, I'm learning as I go because I've done this for 3 years, but I will admittedly say that I still don't know much. But I love doing this just because I love learning spooky physics. So I would really appreciate if you subscribe. You'll get more content from me, I promise. And you can, come along for the ride. And who knows, if you're starting physics this year, if you're studying quantum physics, maybe you'll have an edge. I don't know, I hope. I certainly didn't have this at the time when I was taking quantum physics. I would really appreciate it. So yeah, subscribe, and I've also got an Instagram account. I'll leave a link in the description for that. And yeah, so I hope you guys enjoyed this video. So peace out.